Hello, I'm Pam Hoffman, Everyday Spacer.
I'm Jeff Miller, 2049 Outfitters.
At Everyday Spacer, we show regular folks how to personally and directly participate in space exploration, science, and astronomy. We're here on Friday nights at 9 p.m. Pacific Time, 12 midnight Eastern Time, and 2 p.m. on Saturday in Queensland, Australia. We're broadcasting live from Thousand Oaks, California.
And tonight's guest is Larry Bartoszek, and we'll be back in 8.3 seconds. Larry Bartoszek has a dual degree in mechanical engineering and physics from the University of Illinois, and is an Illinois licensed professional engineer. He's a member of the American Society of Mechanical Engineers, the American Welding Society, the ASM International, the Chicago Society for Space Studies, the National Space Society, and is an NSS Space Ambassador and the International Space, and is involved in the International Space Elevator Consortium, and a lot more. But you came to hear from Larry, not me. So we'll be presenting him. I saw Larry at the ISDC last month, and I thought he'd make a great guest.
Absolutely. And hi, Scott. Welcome. He says, hello, Pam, Jeff, and Larry. Awesome. So, Larry, tell us about yourself and how you got into space exploration. I know you want to talk about something else, too, but go right ahead.
Well, in 2004, there was, if I'm not mistaken, there was a government shutdown during that year, and I started, my payments started slowing down because I do contract work for universities and national laboratories, and I saw this book back in 2004, The Space Elevator, and I read it by Brad Edwards and Eric Wessling, and I was completely hooked. And Brad describes a process of deploying a space elevator and then reinforcing a space elevator with construction climbers. And I'm a mechanical engineer. I recognize an electric vehicle. The main difference is this electric vehicle goes straight up. And to my knowledge, I'm the first person who wrote the free body diagram for a climber and started figuring out the kind of torques and motor characteristics, and then doing basic mechanical design for climber designs.
Dawn's here. Hey, Dawn. She says, hey, folks, welcome, Larry. Yay, we're glad you're here.
So that's how I got into space. Now, that's not my day job. My day job is working with nuclear and high energy physics experiments. I design experiments for governments, national laboratories, and universities all over the world.
Yeah, like for 30 years now, right?
Ever since I graduated from the University of Illinois in 1983, I spent 10 years at Fermi Lab. And then I started my business in 1990. And in 1993, I had to quit Fermi Lab because I had too much business.
Oh, no kidding.
Yeah, I couldn't do a 40-hour-a-week job or more, and then all the consulting. So I just decided to do the consulting. And
that sounds like a good problem to have.
It's been a wonderful career in the sense that I've avoided tons of management. Back when I was a young mechanical engineer, an older mechanical engineer told me the first 10 years of a mechanical engineer's career is all technical. The second is a mixture of technical and management. And the third is all management. So I quit. I've only done technical ever since.
Oh, okay.
Got it. All right. Yeah, you had a ton of stuff on the bio that you gave me, and I'm thinking we will definitely want to have you come back and talk about other things. But you queued something up for tonight, right?
I queued up there's a PowerPoint presentation available from my website that gives all the projects I've worked on as Bartoszek Engineering over the years, and we can talk about any one of those. Or I also queued up the PowerPoint presentation from ISDC about delivering power through laser to the climbers. But I'm willing to talk about whatever anybody wants to talk about.
Hey, Janie, welcome. She says, wow, what an accomplished gentleman. Welcome. Great mentor. Yay, very cool.
Thank you. I've done FIRST robotics as a hobby.
Oh, that is it with the kids?
Yeah, boy,
Oh,
that
that's
is exhausting and uses every second of your life.
Yeah,
I bet it's great though.
yeah.
It's a lot of fun, and I love the kids.
Yeah, my nephew's in high school now, and even starting middle school, he was doing robotics. So
Yeah.
yeah.
Yeah, very brainy kid. I guess above Mensa even. Amazing.
But yeah, it keeps them interested. One of the things with your powering the elevator with lasers, just why not briefly say why you would want to do that? I mean, why not just run cables?
Okay, it's an excellent question. And if I could just bring up one picture.
Yes. Tell me when you're ready. I'll share.
Okay.
All right. There it is. Oh,
Ready.
there it is.
Yep.
So this is a single climber about 30 meters off the deck of the launch platform. And these are two laser transmitters. And the real answer to your question is that once you get above something like some tens of meters, something like an extension cord really doesn't work because this thing is requiring thousands of amps of current to drive the motors that make the wheels roll up the tether.
Yeah.
So
and you can't just run that have two cables, one positive, one negative.
So we are actually we just started a study 2 weeks ago about how do you power the climber, and we're looking at all of the options. We're looking at laser, we're looking at microwave, we're looking at what do you beam it from space, do you beam it from the ground? There's some more unusual ideas for launching a climber, like perhaps stretching the tether, putting elastic strain in the tether, and then shooting the climber up like a rubber band. That one is going to require a little more simulation to determine the sensibility of it.
Yeah, how many G forces or change of G forces do you get? What's the jerk on that? Not just the acceleration, but the jerk.
Exactly.
When you're brainstorming, though, you want to keep all those because you never know what it will generate out of that. Thinking about it, and Cliff is here. I'm gonna just, hey Cliff, sorry about your internet. Glad you're here though. Cliff is in Australia. Yeah, I listened to your ISDC talk, and I'm shocked that they gave you only 20 minutes to work with. But it was excellent. I really appreciated that, enjoyed that. I meant to get Scott has a question. I'll go ahead and flash that right now. You want to read it, Jeff?
Yeah.
I'm going to look
Scott
for that.
Says, how do you keep a space elevator from being a giant lightning rod? Or do you turn the lightning strikes into a usable energy source?
Oh, there you go.
Yeah.
What a great question.
That is a great question in the sense that when Brad wrote the book, he searched all over the world to find the most boring weather on the planet. And it turns out along the equator, right just east of the Galapagos Islands, that is the dullest weather in the world. It's the lowest average wind speed. It's the lowest probability of lightning strikes. And the tether that we're imagining right now, if it's made out of graphene, is actually an excellent electrical conductor. And people have asked the question, will it discharge the ionosphere? And that is an excellent question, but we think the effect is mostly local. And one of the reasons we think the effect is mostly local is that it's not a perfect conductor. It's better than copper, but over long distances, it will still dissipate power. So that's one of the challenges of using the tether to conduct. We're talking about the distance between the surface of the Earth and geostationary orbit is 36,000 kilometers. So you can burn up a lot of power in something that's not a superconductor over that length.
Oh, so there's a lot of I would call it like mechanical loss, right?
It's electrical loss. The conductor heats up.
Right.
Now, we do have a group that is trying to analyze to see whether or not if you use 1 megavolt and high frequency, can you reduce the losses? And it looks promising, but it needs 2 tethers. And with 1 megavolt voltage difference, the tethers have to be insulated from each other, or there would be a massive flash of lightning with that.
Right.
It's so interesting you talked about the place that was the calmest, because I know there's another place on Earth, and I'm sitting here going, are they opposite each other? That has like lightning strikes almost continually. It sounds like it's crazy.
No, they're not opposite each other. They're both South America, just different sides of South America.
I see. Okay. Interesting.
Yeah,
because I can't remember where the other one is.
You don't want to build a space elevator in the other one.
No.
That's interesting. There is a place that's that calm. It's very, very calm.
Well, unfortunately, what the vision of the International Space Elevator Consortium is what's called the Galactic Harbor, which has 2 space elevators in each of 3 sections around the world, not necessarily equally spaced, but so you'd like that effect all over the world, and I don't think you find it all over the world. So that'll be an interesting question.
Yeah, you wouldn't really be able to plant one off of Florida or anything like that.
Yeah, I know the idea has one in the Indian Ocean, and I'm not sure there are monsoons and things like that there. So
yeah, are they still looking at? I think there was some thought about having it at the equator, basically, or is it?
It has to be close to the equator.
Mm-hmm.
It has to be. Yeah.
Okay.
You can talk about a few degrees plus and minus north and south, and it introduces an interesting curve to the tether, but it makes you a longer tether.
Mm-hmm.
Oh, interesting. What about at the poles? Because aren't they a little bit? I don't know. Less.
So a space elevator does not work from the poles at all.
No kidding.
What holds a space elevator out? Pretend I'm the Earth. And I have a string wrapped around my belly, and the string is dangling down in front of me, and it has a rock.
Like a loop thing. Yeah.
If I start spinning, what happens? The string begins to stretch and fly around in the plane of my equator. Okay? And an ant can walk along that string and out into space. So so literally the tether uses the centrifugal effect to stay straight and to stretch out into space, and then anything that's on the tether gets the angular momentum it needs to be in geosynchronous orbit from the tether. So you're literally stealing some of the rotational energy of the Earth.
Could you steal so much that it would stop the Earth at some point?
It would take a very, very, very long time.
Got it.
And if you're sending cargoes back down, you end up imparting some of it back too.
Oh.
Yeah.
Okay.
There are all kinds of interesting problems associated with allowing cargo to come down the elevator, because if you look at the talk that I gave on powering the climber, you see how much energy difference there is between the surface of the Earth and geosynchronous orbit. You're pumping that energy in to make the climber get to geo. You have to dissipate that energy when the climber comes down, and we don't actually know how to do that at the moment.
Was that the ISDC? Because I have that link here. I can share it in the chat, and I believe it'll be a clickable link for you folks who would like to see that. I definitely recommend watching that. It was very, very good, if condensed quite a bit.
Well, here's a thought, but it would require tech that we don't have. Much better power density batteries than we have.
Oh, that would make everything easier.
Yeah, because then you could build the unit up on the top of the tether, send it down, and have it just generate on the way down. But anything that we have now would either be way too heavy or would explode about 1/10 of the way down.
Yikes.
Yeah. There's for every kilogram is 53 megajoules of energy. So a 20-ton climber is a terajoule of energy.
So a thought that I just had in the back of my head.
Here we go.
Was just thinking about it as a thought project as we were talking, of a bunch of people on running pedals to gear it onto the No go, huh?
There is a proponent of an idea to have a loop of tether, so the climbers don't actually climb; they're just clamped to it, and
Mhm.
you have a sprocket near the Earth and a sprocket up in space,
Oh,
and
I see.
you make the tether go back and forth, and it counterbalances the way an elevator has a counterbalance.
Sort of like a bicycle chain.
Right.
Okay.
I like the idea of a bunch of guys pedaling themselves into space myself.
It's just a little wacky.
I mean, or you get a Roma sitting there, and they're all in benches with oars.
Well, so that's the other thing about the early deployment of the space elevator. We're not talking about people for a couple of reasons. Number one, the trip takes a week to go from the surface of the Earth up to geosynchronous orbit. The maximum speed is only going to be a few hundred kilometers an hour, so people would get bored, and they would have to.
They take cruises.
Well, they'd have to do things like eat, right?
Yeah,
so you'd have to bring a lot of supplies along and air. But even worse, most of the distance between low Earth orbit and geosynchronous orbit is the Van Allen radiation belts. So you need a lot of shielding to keep them from dying on the way up.
Okay.
Yeah, so you probably want a faster way up than that.
Yeah.
That's why we talk about the dual access to space using rockets and the space elevator.
Yeah. Or, heck, the old long cannon.
Or what they've just built in New Mexico, spin launch.
Oh,
I haven't heard about this.
There's a centrifuge that can spin a missile-like projectile with a tungsten tip up to a speed fast enough that it can get into orbit. And of course, because it's a centrifuge, if you release one thing on one side, you have to release an equal and opposite thing on the other side, or you'll destroy the centrifuge.
Yes.
So they have a dump where they blow stuff into the ground as they're shooting the projectile out.
Okay.
There's a great video on YouTube of spin launch. Very interesting stuff.
Spin launch. Okay, we'll have to look for that. Cliff's, yes, it would take a long time pedaling. Probably more than a week. So, do you have like any kind of idea or projections when this could become a reality? I knew some people, Michael Lane, I think it was, working on it, and I guess they ran into some real problems, and they're like, yeah, it's never really going to work. But
he was laser launch, right?
No, that was Jordan Kerr.
Well, no, there was someone else too.
Michael Lane was working on space elevators, and I don't know if he's part of the consortium or a different group, but
different group.
Group.
Liftport is his company.
Yes, Liftport. That's right.
So you know the old joke: how do you make a small fortune out of a space-based business, right?
You start with a bigger fortune.
Start with a large one. I think that's pretty much what happened to poor Michael.
I see. Okay. They really ran into some technical problems, didn't they?
Oh yeah. Well, the whole project is waiting on the material of the tether, because you need a material that's roughly 200 times stronger than steel to support its own weight between the surface of the Earth and geosynchronous orbit.
Got it.
Material like this stuff.
Yeah.
This is a model of a graphene, 3 layers of graphene. And
it's very light, isn't it?
It's very light. It's very, very strong in the plane where you have covalent bonds between the carbon atoms. It's these purple bonds between layers that are van der Waals bonds, which are not as strong. And we discovered in our in our 2023 study that actually the shear strength of multi-layered graphene is too low without having some kind of cross bonding. And basically the problem is that if you get friction from the wheels on the outside, the wheels want to shear the outside layers with respect to the inside layers.
Huh.
And that shear force does not transmit well through multi-layered graphene sheet. So we have to figure out a way to cause some of that cross linking from layer to layer.
Yeah, it would also seem that even without running a vehicle up it, that just wind moving it slightly like this, you'd have one side essentially stretch relative to the other, and that would also cause that same shear force.
Well, you're right, but we're talking about a film that is possibly 10 microns thick.
Oh, okay, yeah.
So it's thinner than the aluminum foil that you have in your kitchen, and bending shear forces, like from rolling around a reel, are nothing compared to the kinds of traction shear forces you get from two wheels that are squeezed on opposite sides.
Yeah, as it's trying to haul something up it. Yeah.
Sounds like a composite. Sounds like a composite may be in order. Something with that and some other things.
More weight. Yeah, that's the trouble.
Oh, you got something to show us?
Well, I'm not. I'm still sharing, but you're not sharing my whole screen yet, right?
Not yet. You let me know when you're ready.
All right. There is something called an Ashby plot, which would be useful to bring up, because an Ashby plot basically plots the strength of materials for every single material as a function of density. And that's what's really important for the elevator material. And I've given a lot of talks on the conceptual design for the climber based on our, here's a good one. Conceptual design for a 2010 climber.
I'll go ahead and share.
Okay. So an Ashby plot, I'll get there in a second. There we go. That's an Ashby plot. So this is a plot of all the materials that you can think of. It's a function of strength versus density. And you can see the foams are very low density, but they're also very low strength. All the natural materials like woods are in here, and metals are in this orange region. Ceramics and composites are in this region here. And there's an interesting material. So aluminum alloys fall in this little oval right here. So they have reasonable strength, and for their strength, the lowest among the lowest densities. But another material that is stronger and lighter is CFRP, which is carbon fiber reinforced polymer. So when I first started designing climbers, I have a lot of familiarity with aluminum, and I used a lot of aluminum because aluminum has three characteristics: lightest, strongest, cheapest. That it's practically the only metal that you can say all three of those things about simultaneously. When I discovered that aluminum was still too heavy and I started switching things over to CFRP, then I go to this plot, which is, here's its strength as a function of relative cost. So CFRP is stronger, but it's also about 10 times as expensive as aluminum. But it's using something like an Ashby plot that allows you to pinpoint areas of strength and density that might be useful.
Boy, I've never even heard of that. That's a fascinating chart there. Both of them.
You would love to have a material that's in this region here. Really high strength, really low density, but there is literally nothing there.
And it's interesting how they all kind of fit along this linear kind of plane.
And that's what's going on. They are getting stronger on this axis, but they're also getting heavier.
Yeah. So I wonder if there's a way to get to that point in the
over here.
Yeah.
Boy, that's an excellent question. If you knew the answer to that, what I'm reminded of is the hull integrity field on the Enterprise.
Okay. So it's basically nothing, but it's very strong. Right? The hull integrity field. So it's a force field, right?
It's a force field, yeah. I always wonder in the show, isn't it a bad thing if that number is ever less than 1?
Yeah. Yeah.
I don't know.
Well, and Star Trek assumes energy densities that are just essentially magic for us.
Sure. But But if it really is run on matter-antimatter reactors, I've got friends who are working very hard to commercialize antimatter production.
Mm-hmm.
We learned a lot about how to produce antimatter at both CERN and at Fermilab. And the people that I know believe they can do it more economically with a much higher yield of antimatter.
Oh, okay.
You think anyone want to be a guest on our show?
I can ask them.
That'd be wonderful. And I mean, we actually had someone. It was Greg Hodgin, who was talking about You remember Greg?
Oh, yeah. He was talking about fusion.
Well, he had antimatter and antimatter in there.
Yeah.
Like very, very small, microscopic, I think, right?
If you had small amounts of antimatter, you can use it to trigger fusion.
Yeah.
Yeah, that was it. It was a great episode. We have to have him come back too.
Yeah. Yeah, because antimatter is basically a store of energy because you need energy to make it. But then a lot of fuels are like that.
Yeah.
And if you can make it, for example, if you had a satellite that was using sunlight to produce the energy to produce the antimatter, then it's effectively free. Especially if that satellite is in a different part of the orbit collecting light that doesn't go to the Earth at all.
Right. Yeah. And also
there's a lot of that.
I'd rather have it out there than here.
There's a lot of sense to that.
Because kaboom.
Well, yeah, because if you're storing a bunch of it and the power goes out, it's a bad day.
Which kind of makes me think about the space elevator too. You kind of need something that's like, I know on regular elevators, if something goes wrong, they have magnetic brakes, which will stop no matter whether they have power or not, right?
Right.
So,
and
go ahead.
I did a lot of research on brakes for the space elevator, for the climbers on the space elevator. It turns out they represent a significant portion of the mass budget of the climber that's in our conceptual design.
Brakes do.
They're too heavy. They're just too heavy. They need to be custom designed to be lighter so that we're not taking away so much from payload.
Yes. Right. Yeah. I worked at Boeing, and so I know something about payload. We if we took off 100 pounds from the spacecraft, we could add 1 pound of payload. So anything we could do, like paint weight. I mean, they hogged out all kinds of metal in everywhere.
And that's why the shuttle's main tank became orange, because they decided to save, a few hundred pounds of white paint.
Too much weight.
Sure.
Yeah.
But, so couldn't you use the motor as a generator brake for braking?
Yes.
Okay. So there'd be a twofer for mass.
Yeah.
You can do that, but there are scenarios. So one of the things the tether doesn't like is if you jam the brakes on.
Oh yeah, it doesn't like the jerk. Yeah.
If the motor is being used to overcome gravity to raise the mass of the climber, you have to think about how do you turn that into a brake then.
Right. Yeah.
So if you tell me some of the scenarios you might require a brake. I guess getting to the top, you want to stop, right?
Sure. Well, stopping is easy because if you just reduce the current to the motors, they won't turn as fast because gravity will slow it down. Of course, that effect gets lower and lower the closer you get to geosynchronous orbit.
Right.
Some scenarios in which you might want to stop somewhere is, for example, if your climber was doing an experiment at reduced gravity, like if you were doing it at Martian gravity or lunar gravity. Now, blocking the elevator for an extended period of time to do an experiment like that may not be the most economical thing to do as far as putting cargo up. Because that's really the whole point of the elevator, is to increase our ability to move mass into space.
Sure.
Yeah.
Okay. Yeah, and there's various layers of atmosphere that we know very little about.
Oh, the tether would allow you to do research missions to any level you want.
Yeah.
Right. Yeah.
Yeah.
Cool. Oh, so interesting. Are we at all close? Are we talking 10, 50, 100 years?
I hate to sound like fusion,
Yeah.
which is always 50 years away.
Yeah.
But I know people who believe that um, it's all a question of money. If you were to put this kind of funding into it that, for example, the Manhattan Project had, 15 years is not unreasonable to develop the tether material. But we're talking Manhattan Project type money. If
Okay.
you don't have Manhattan Project type money, it's a longer horizon.
Got it. Okay. Interesting. Yeah, it's really will and resources.
But the other
For
thing
almost
is,
anything.
if you've got this material, there's tons of things you could use it for on the
Sure.
Earth.
Yeah,
Athletic
suspension bridges for
equipment,
one thing. Yeah.
military equipment. It'd be fantastic for all kinds of military equipment.
hmm
Oh, interesting.
Now, one of the things that comes up is like the disaster of the tether break, which the stuff that you're talking about is so light. It seems to me like some of it might not even hit the Earth. It might just float.
Oh.
So we've been talking about this recently. An old friend of mine that I met at the first space elevator conference that I went to, Blaise Gassen, did simulations, and what he showed was the elevator is longer than the circumference of the Earth by quite a bit, and depending on where it breaks, it begins to rotate, and as it rotates, it swings and gets faster and breaks in multiple places. So most of it goes off into space, and
Really?
a very small amount ends up falling back in the ocean.
Huh. That actually sounds like a good. Would you call it a failsafe?
I don't know. Well, it becomes less of a total disaster.
Right.
It's certainly an economic disaster.
Well, I mean,
Yeah.
what's your rough guess? Is like a 10-meter stretch of the tether. How much do you think that would weigh?
We have estimates of that. For a 100,000 kilometer long length of tether, we're talking 2 to 4,000 tons of material. So if you had an arm's length of it, it would feel probably I've got a rough idea of the density in my head, but I don't know if comparing it to aluminum foil is correct. But it
Right.
would feel light like that. It would probably feel lighter than aluminum foil.
Right. So its falling force wouldn't be that great. I mean, I'd be more concerned about the elevator cab than the tether itself.
Sure.
Because,
Yeah.
it'd flutter down essentially.
Yeah, I think that's true for the
Part
part
that
that
doesn't go on to orbit.
Yeah.
right.
Yeah. So it's not like in some of the science fiction stories where you end up with this great, strewn, demolition field around it.
Even in Red Mars, by
Mhm.
Kim Stanley Robinson, where they had a space elevator fall, I believe these breaks would also happen in the Martian elevator, so that the disaster that he wrote in that book, where the elevator wraps around Mars, is probably not what would happen.
Got it.
Yeah.
Okay.
Yeah.
I haven't read that one yet.
It would have a faster falling speed just because there isn't as much atmosphere. But
Not as much gravity either.
well,
Right.
Yeah.
Right. That's an interesting. You'd have to calculate.
Yeah.
Yeah. I'll leave that for an engineer.
Well, it's all really fascinating. Thank you so much for. Wow. Okay.
But that's what, for me, that's the intellectual challenge, right? You
Yeah.
looking at. It's also forced me to look at all the various modes of transportation that we have on the Earth, like locomotives. Could a locomotive with that kind of motor power climb straight up? And the answer is no. Locomotives have a hard time doing certain hills.
Right.
Their
Well, it's
their
a 6%
motors,
grade is high.
yeah,
Oh.
their motors are incredibly heavy. So
And they rely on smooth metal against smooth metal friction. So you
Yeah.
get too high and they just spin.
Mm.
Yeah. But, even so, even if you could transmit that mechanical energy directly to it with some kind of sprocket system, it's still, it's not a huge huge amount of energy there.
Turns
The one
out
thing go ahead, Larry.
the friction that you're talking about is one of the big problems with the design of the climber, because
Right.
this material, the graphene, is probably going to give us a very low coefficient of friction, 0.1 ish,
Oh.
and that drives everything about the climber.
Mm-hmm.
It tells you how hard you have to squeeze the wheels together to get
Mhm.
enough traction to hold the load. And so that determines dynamic stresses on the wheels and on the axles and on the bearings. But it also determines the static stresses, because other parts of the climber have to react that compression load as a tension load.
Mm-hmm.
Ah, one of the things I like about laser powered things is a lot of the infrastructure is on the ground. It doesn't have to be in the cab itself.
That's what's supposed to make the space elevator so much more efficient than rockets. It doesn't carry its own fuel.
Right.
Yeah, you had a really cool graphic about it was something about the angles and not having to worry so much about the reflection.
Or shadowing.
Yeah.
I've been worrying a lot lately about shadowing. Here's a picture of what happens if you try and put 5 20-ton climbers on the tether and deliver the power to each one of them.
Oh. Uh-huh.
So I have a circular pattern of pairs of lasers, and what I noticed when I was doing this CAD model is this PV array right here can begin to shadow this PV array up here unless these two climbers are the right distance apart.
Right.
And you notice as you get more and more climbers, they have to get further and further apart to avoid that shadowing effect. Yeah, we're working out all of those details now. This is just an early concept sketch.
Oh, got it. Okay, but that was part of your ISDC talk.
Yeah.
And we've got Happy Place. Thanks for joining us. I think you've been here before. It goes, anti-gravity tech will likely beat out space elevator tech.
You are absolutely right. And as soon as you get a
Really?
handle on that, patent it.
Yeah.
You'll be a multi-trillionaire.
Well,
right?
Yeah, because then it would beat out anything else for getting up into space. But
Right.
we know at least how to start making a space elevator.
Right.
That's the.
Well, we know the other one too. You just throw yourself at the ground and miss.
Over and over and over.
Yeah.
Well, that's how someone described reaching orbit.
Which
Right.
Yeah, throw yourself at the ground and miss.
Oh, you know what that's from, right? It's Douglas Adams.
Yeah.
Hitchhiker's Guide to the Galaxy.
Yeah. Yeah. I forget which book it's in, but yeah.
But yeah, I mean, a lot of the things that I would think of, if we developed this to incorporate into a space elevator, well, if you developed that, you wouldn't need a space elevator, type of things.
So I'm just curious, Happy Place, do you know something we don't? Is there a consortium out there doing anti-gravity tech work? I would love to have him on the show as a guest.
Absolutely. I'd like to know all about that.
And we look at how many different ways we have of getting around now. We've got airplanes, we've got cars, we've got buses, we've got trains. I don't think there's going to be one versus another. It's going to be, which one do you prefer? Some people do not like to take planes, so they're going to take a train. Or can you afford to take a suborbital hop? Yeah, it's all a matter of preferences and
economics. Sure.
Yeah, absolutely.
I just had a thought, because we know someone who does airship to orbit.
Mm-hmm.
Of what about having a lighter than air component to this?
Ooh.
It only help you up so far, but that'd be
it.
in the heaviest, that'd be in the highest gravity zones of it.
Well, but they're talking to going to Mars.
Right. No, but I just meant as something to help reduce the load on the space elevator.
So
interesting idea.
So the thing about the atmosphere is it's 0.3% of the length of the trip.
Oh, okay. So it's not.
And the highest stresses in the tether are up at geo, because the material at geo is supporting the strip of material below it,
Right.
and it's also supporting the strip of material up to the counterweight.
Yep. Yeah. So
Okay.
you're not as concerned about near the Earth as you are up there, huh?
I've never seen airships as adding a significant contribution. Not only that, the higher you go, the less payload they're capable of.
Right. Yeah. Yeah. I was only. You see. Yeah. I guess I'm thinking of the rocket thing where you have to go really fast and you're pushing a lot of air out of the way. So, just having something that would let you go slower up through the atmosphere.
Yeah, I don't think an elevator would do that.
Yeah, would care. Yeah.
Yeah.
You're not going fast enough to.
That reminds me of a book that I read as a kid, The Mouse on the Moon.
Oh yes.
Oh, I don't know.
They had an energy source that allowed them to raise their ship very slowly and continuously.
Yep.
I don't remember the details of that power source, but that's kind of what you're talking about.
It was chemical.
Okay. So somehow they got around the rocket equation for that one.
Right. Well, and this was, this was back in the era when, launching people to the moon with a cannon was considered a viable concept. And they didn't think about, okay, so how do they get off the moon then?
That's a very good point.
It's a one-way trip, it sounds like.
Yeah. Well, and they did. Jules Verne did actually figure that if you get a long enough cannon, you don't turn people into paint on the bottom of the shell.
Okay, Happy Place comes back with, obviously, people and companies are working on anti-gravity techs. Okay.
Oh, yes.
Some stuff has been patented and scooped up by the Department of Justice. Justice? No. Department of DOG?
Department of Energy.
Okay. I'll email you some references. Oh, well, thank you. Love that you're here, Happy Place. Thanks for joining us.
I would like to hear
Awesome.
that too.
Yeah, I didn't know. I had not really heard of anybody working on anti-gravity anything. So.
Well, there's a lot of people working on stuff, but is it real? I don't know. Yeah. Like the M drive and things like that. People talking about quantized inertia and all kinds of ideas.
Yeah, there's a lot of PhD students doing papers.
Yes. We called it cartoons at Boeing.
But, hey, if someone's actually bending metal on it, they might have something on it. So
yeah.
The problem is if your thrust is so low that it's hard to tell from noise, that's a difficult experiment to prove out.
Yeah. Yeah, because a lot of these have shown up to be just noise.
Right.
So Daniel has joined us. Thank you for joining us, Daniel. You simply need to build a lunar return cannon after you arrive. Okay.
Or you do what Elon Musk wants to do, is you shoot robots there first that build it for you so it's ready when you get there.
Right, yeah, Robert Zubrin has sort of the same sort of idea on Mars to go and get stuff set up and generate oxygen and be all ready for you to move in when you get there.
Well, my thought is on the moon, you use maglev trains. And then all you have to do is make a straight section on it, and you can use that to launch.
Moon is a harsh mistress.
Yep, that's exactly where I was going. You might want to be careful how you aim those suckers when you build them.
Yeah. That is actually a kind of a touchy point about the whole asteroid return business.
Right.
Oh.
Yeah, we've had asteroids return to Earth before.
Yes, that's true.
The dinosaurs didn't like it much.
It was good for us, though.
Yeah. So.
All right, Larry, do you have anything else in your various and sundry slides there that you want to share with us?
Oh, well, one of the things that I could show from this one presentation about climber design is something that has turned into a really challenging issue. Um, that's the picture.
You ready?
See this blue shell?
Yeah.
Oh yes.
So first of all, this is the concept design for the 20-ton climber that we worked on from 2020 up to 2023 when we released the study. And in this study, I finally chose what I thought was a reasonable first customer for the climber. And I said, okay, um, look at the amount of liquid oxygen Elon Musk needs to move starships to Mars. And he is talking about refueling them, as he calls it, refilling them in low Earth orbit. But what the space elevator would be really good at is developing a fuel and LOX depot at GEO.
Mm-hmm.
So this tank is a 5-ton tank of liquid oxygen, and there is another one on the other side. So there's two 5-ton tanks of liquid oxygen. For this design of the climber, with some finagling, I was able to get about a 50% payload capability. That's never enough for the people my colleagues at the International Space Elevator Consortium. They'd like to see a 70% payload capability. You know, I would love to too. I've just never been able to get it anywhere close to that. But one of the things that I learned during the process of developing this design is that these motors would have to be liquid cooled. The bearings on the axles are also recirculated lubricant. None of those materials can really stand a temperature over 200 C. So any of the waste heat, and if the motors are 96% efficient, I'm talking about a waste heat on the order of, I think I said something like 160 kilowatts. Yeah, 160 kilowatts. If the motor's running at its peak efficiency out in the vacuum of space, you still need to dump 160 kilowatts.
Mm-hmm.
And the only mechanism you have to do it is by thermal radiation.
Right. Yeah.
So you have to have a space radiator. And thermal radiation is not terribly efficient.
Right.
So this light blue shield is the area necessary to dissipate 160 kilowatts near Earth, because when you are in near Earth orbit, the average temperature of space is not the lovely, balmy 3 Kelvin that it is far away from planets. It's much warmer than that. So you get an even reduced ability to reject heat. So dumping low-level waste heat turns out to be a much bigger problem than I ever expected it to be. And I never even bothered to develop the plumbing that would recirculate fluid through the thermal radiator and all that, because it would be a lot of effort. I mean, for one thing, I don't get paid to do these designs. This is what we call hobby.
Mm-hmm.
But
Right.
what I'd like to do eventually is come up with a refrigeration loop that allows me to increase the temperature of the space radiator without increasing the temperature of the lubricants and liquids that are cooling the electronics and the motors. And
Right.
I think if I can make this space radiator hot enough, I can make it small enough to be more practical.
Mm-hmm.
Well, you got some interesting problems in your hobby.
Yeah. Yeah. The main thing is and then transporting that heat. Although that's not as big of a ask as getting a really hot radiator, because, well, actually it is, because you have to transmit the heat in one direction, not both. Because if the radiator is that hot, how do you keep it from coming back to the?
Well, that's what a refrigerator does. You
Yeah.
put work into the system to segregate the heat into different components.
Right.
And I believe the amount of energy that we would have available to us from the laser beaming would be plenty to run a refrigeration system.
Oh,
Okay. Yeah.
wow.
You just definitely want the radiators shadowed by the laser receivers.
Exactly. So that's a very interesting point that you see in this picture down here.
Oh, let me share. Hold on.
You notice, first of all, these PV arrays are very small and they're overlapping the heat shield, the radiator.
Yeah.
You wouldn't want that. You wouldn't want that. What I figured out later and what I show in the power beaming study is you want like 5 meter diameter receivers and you want them mounted far enough away that the beam is not heating up your space radiator.
Right. Yeah.
But what does that do? That means you've got arms that are made out of something that takes away from payload.
And, and they have to be stiff enough to hold them at least in Earth, in 1G.
Exactly. 1G of gravity, because up until pretty far up, they're being weighed on like everything else on Earth. Not only that, this model in particular, and I have friends who are trying to argue me out of these rotary joints. There's a yaw joint here and 2 pitch joints to be able to point these PV arrays at each of these different pairs of lasers. That means there's a flexible coupling which is carrying thousands of amps of current across all of these rotary joints.
Here's something, and I don't know if the effect would be big enough to be noticeable, but you use a metal or composite that is flexible enough that it will droop in full G, and as it goes up, it would droop less and less. And that would give you different angles on the things, but I don't know if the angles would change fast enough for it to make any sense.
What you're talking about is perfectly sensible because there are 2 different types of mechanical designs. The one type of design is a design based on strength. Okay,
right.
The critical element is it strong enough that it's not going to break or it's not going to deform too far.
Right.
The other one is a design by deflection, and in designs by deflection, you can't let the parts move very far.
Right.
So there, the stresses are always low. Yep. And what you're talking about is making the arms a design by strength where those small angles of deflection at higher loads don't really matter to the laser transmitter. They represent small cosine theta errors between the laser beams and the PV arrays. So that's perfectly reasonable.
Yeah, because I mean, I used to fly a lot, and I know that at least on the bigger aircraft like the airliners, the wings droop when they're not, basically being pushed up by the airflow.
Sure.
And they're designed that way so that they don't snap. But I was thinking maybe you could put that effect to use and not have to design as much strength into the beam itself.
We would do that. What makes those airplanes work that way is very low safety factors, like 1.5, and that's definitely a design for strength, not a design for deflection.
Right. Yeah.
Daniel came in with a comment. I heard NASA has to fix the overheating lunar rover motor issue days before launch. They're surrounding them with solid paraffin in boxes that liquefied during use and rehardened for the next use. This is had. I don't know where the had goes.
I've heard of that, and it's using a phase change to absorb heat. And then you dissipate that heat out through some other mechanism, it rehardens, and then you can use the material over again. And the refrigeration system that I'm talking about for the climber would also involve some kind of phase change. I haven't been able to figure out what material would do that for me. The Parker solar probe that cools the PV arrays on that satellite, which is heading, which is near the sun, uses water. So water is not unreasonable. Water has a huge specific heat.
Right.
Mm.
Yeah.
Okay. Cool.
Because I know that like for solar thermal reactors, that they talk about using salts as in a phase change, for grabbing and releasing the heat.
Mm.
So that that phase change is like huge heat difference.
Yeah. Got to break all those bonds.
Yep.
Well, this has been awesome, Larry. Thank you so much for being here with us. And folks, if you have more comments, we definitely want to hear from you. Anything else you want to share with us? Because we do have a couple more segments, and then we can wrap it up. And if you would like to come back and talk about something else, I mean, we love crunchy topics.
Do you notice we were just talking about chemistry? We were talking about thermodynamics.
Yep.
We were talking about machine design. I mean,
Yep.
there's just so many interesting aspects of this whole problem.
Yep.
Yep.
Well, and
getting paid would be nice too, right?
And you never know what else you get out of it. I mean,
yes.
If you make a solution for this, that even if it doesn't work for this, might work for something else.
Well, it turns out I based the design of the motors on the climbers off of currently available motors for electric aircraft. If I get even more powerful and lighter motors, you get better electric aircraft.
Yep.
There's actually a thing as electric aircraft.
Oh yeah.
Okay.
People are trying to electrify everything.
Yeah.
Yes. All right.
That from the point of view of the everyday spacer, we can all do this stuff. You use whatever skills and knowledge you have to develop whatever interests you.
Right.
Yep. Oh yeah, we have people who are artists, and there's all kinds of ways to participate. You can join. You can compete. Join a competition for things, win some money in some cases. There's all kinds of different ways. Oh, we got a comment. All right. So let's see. Happy Place says, disregard if already answered, but how do you connect the orbiting station back down to Earth? And I haven't heard that yet. So good. Thank you.
So this book has what Brad came up with for a deployment scenario. And his original idea was you would take up two spools of the carbon nanotube material. He was working with carbon nanotubes instead of graphene back in the early 2000s.
Right.
And he planned everything around the cargo bay of the space shuttle. So the space shuttle would boost the stuff up to low Earth orbit. In low Earth orbit, you would build a spacecraft that you would use the lasers that he was already planning to power the climbers. You would use those lasers to power an electric spacecraft between low Earth orbit and geosynchronous orbit. Once you get to geo, you begin to unwind the spool of cable. So part of it goes towards the Earth. The reel goes out where the counterweight is going to be. And eventually what happens is the end of the tether, which is gravity stabilized, appears in the atmosphere. You put some kind of transmitter on the end of it so boats can find it. And you go out there and you grab it and you attach it to the base platform that you have in the ocean.
As close to the equator as you can get, right?
As close to the equator as you can get.
Yeah. Wow.
Disturbing the flora and fauna of the Galapagos.
That sounds like a great book. Oh, and you know what? I need to show your website too. But I'm going to have Daniel has a comment here. Don't the grid fins on Falcon actuate with off-the-shelf Tesla car motors?
Oh, I bet they do. I mean, that's exactly the kind of thing I would believe Elon would do.
Oh, yeah. Yeah, well, in fact, I know someone who was building rockets back before, Elon got into it. Rocket motors that were using VW wiper blade motors to, in order to switch the...
what was that?
Harrison, I think.
Oh, I could tell you stories about what physicists do to make experiments work using the cheapest possible materials you can imagine.
Yeah.
I see another comment, but real quick, if you want to reach out to Larry, here is the website, bartoszek.eng.com, right?
Sure.
Excellent.
I'm happy to answer questions by email. My email address is there.
Great. Okay. And your one, I think they mentioned on that page too, is the 30 years of projects. And boy, I scanned through some of that and it was just amazing.
I've had a lot of fun over the years.
Yeah.
Happy Place has another. Won't it burn up as it's being lowered into the Earth's atmosphere?
It's going very slowly.
Right, yeah.
You're not dropping it like a stone. You're unrolling it.
Right.
So it's a controlled entry.
Okay. Right, yeah. It's not, you're not going to have friction heating because it's...
Right. It's just moving too slowly.
Yeah.
One of the things that comes up a lot when people talk about space elevators is, taking advantage of it going through the magnetic field of the Earth.
Ah,
As it's,
so the space elevator, because it's basically got a point on it at geostationary orbit, it's not moving with respect to the Earth's magnetic field in a significant way.
Oh,
okay.
okay.
Okay. Interesting. See, a lot of things have changed since I kind of touched on this before. And like I told you, Lane was one of the people, and there were a couple other people too.
Yeah.
But
Well, yeah, and one of the things that I've seen, and it wouldn't work on Earth, but for places with low or no atmosphere like the moon, using a spinning tether.
oh,
There's so many varieties.
Yeah.
yeah, they talked about that for Mars too. Like,
Yeah.
Is it getting to Mars? Is it?
The experiments that have been done around the Earth in low Earth orbit, because those tethers actually are spinning with respect to the magnetic field, they can develop high enough electromotive forces in them to burn themselves up.
Oh. Wow.
I think there have been some problems with tether experiments suffering from exactly that.
Oh.
So you need a regulator of some sort to.
Some kind of load that would dissipate the current. Yeah.
Yeah. Or do it someplace like the moon, which doesn't really have a magnetic field.
I think the people who are doing it in Earth orbit were actually trying to use it as a power source.
Right. Yeah. That would be my guess.
Oh, I guess we got another comment from Daniel. He says, I want to make a network of automated buoys and zip lines around the equator. I don't know how to say that.
Sequatoria? What would that be for, Daniel?
It sounds like a sporting thing.
Well,
zip lines, right.
To zip line, what? Circumnavigate the Earth via zip line?
They've had people jump from out there to the Earth. So yeah, different sports.
Oh, there you go. More sport, more interest for the space elevator. Have competitive diving off of a space elevator.
There it is, Sequatoria, for research and habitation.
Speaking of fun with space elevators, there have been a number of space elevator competitions.
Oh yeah.
With models, small scale versions.
That's right. Yeah.
I believe the last one was in 2010.
I was gonna say it hasn't been for a while, right?
Yeah.
Well, in fact, I didn't actually see the competition, but I think I saw the vehicles either before or after the competition it was either ISDC or another space conference like that was in LA. I saw like 4 or 5 different vehicles.
Oh.
And tethered designs.
Thanks for joining us, Janie. She says, thanks, guys. Great guest. Celebrating Story Moon. Yep. Blessings for a wonderful weekend. Thank you. And Larry, you sound like you had something to say too.
When we had the ISEC annual conference in Seattle, we used to partner with the Air and Space Museum there in Seattle.
Oh, cool.
And they would rig up a nylon tether off the ceiling, and kids would do Lego climbers.
Oh, I think I heard about that.
Oh, that was so interesting and amazing to see.
Did the kids make them right there? And
not necessarily, no.
Oh.
No, they brought them from having made them somewhere else. I don't think they were made during the conference.
Oh, so sort of a design, maybe competition of some sort.
Design, build, test,
Yeah. Oh, how cool is that?
Yeah, I was at the 2013 conference in Seattle where they did that.
Anything interesting out of that?
Well, as a mechanical engineer, one of the questions I ask young mechanical engineers that I interview for jobs is, what kind of toys did you play with as a child? Personally, I find Legos to be kind of limiting.
Right.
But when you can build a space elevator climber out of Legos, that's pretty incredible. I mean, I'm so old school. My toy of choice is right here.
Yes.
Yep.
Erector set.
Yep, I remember those.
Yep.
Well, I mean, any kind of engineering is going to have its limiting parameters. This one goes up, but that one comes down. Efficient. There's all kinds of opposite things.
And one of the most important things as a kid is to understand about the media that you're working with. What are its limitations?
Mm-hmm.
How big a thing can I build in it?
Yeah, we've seen some stuff about this young man who had, what did he actually lose? He created something for his arm to replace his arm. Has an actuator and everything. It's like, holy smokes.
Well,
out of Lego. His first one
right.
was out of Lego.
Didn't work well, but it was there. You know, he made
That's
it.
cool. It's still cool.
It's very cool. Oh, thanks, Cliff. We really enjoyed this too.
Oh, and Daniel has it.
Oh, I missed one. Sorry, Daniel. Gilbert chemistry set as well in Mattel.
Sure.
Thing Maker.
I still have both of those things.
Oh my word! I never even heard of a Thing Maker.
Oh, thing makers were great. You'd have molds of bugs or other things, army men, and you pour this goop in the mold and heat it up, and it would solidify into a toy.
Yep.
Oh my
god! And they had some that were edible.
Yes.
Okay.
I had one.
That's amazing. That's
Finding
amazing.
the plastic goop for those is a little bit tricky now, but it can still be done.
Yeah.
Wow. Well, all right. We're going to keep watching for comments. I'm going to go through our next segment here, and it's basically some stellar events this week. Oh, we got a comment already. Let me do that first. Easy bake oven for boys. That's good.
Yeah. My easy bake oven was
oh boy,
was making thermite.
Yeah, I had a feeling we were going there.
Oh yeah. Yep.
Or wondering
the pan made out of.
Yes, well, wondering why people would put a magnesium pan in an oven.
Right.
Because I've seen magnesium burn.
Yeah,
and as a kid, I was thinking, this is a really bad idea. So I spent most of a summer trying to light a magnesium pan.
Were you successful?
Let me put it this way. The hole in the pavement was about this big, and I had a sunburn through my shirt. Because that produces an awful lot of UV.
We had a lunch conversation at Fermilab once where we were all sitting around the table talking about what kind of influences we had when we were growing up, and we realized that we had all experimented with explosives as children.
Yep. Oh yeah. Yeah. The best boom I ever had was just a big leaf bag over a car battery and breaking water into it. Just get the right mix, because you put it over. Yeah, you just put it over both poles and then lit it, and yeah, it basically hit you like a big giant pillow. No slap. It was just like being hit with a giant pillow. Because we ran, but not far enough.
That would be hydrogen burning without quite enough oxygen.
Right. Yeah.
When you have enough oxygen, there's nothing gentle about it.
Oh, okay. Yeah.
Yep. We had some really good comments about 3D printing, and is 3D printing going to be helpful to you in solving some of your issues?
We've begun to use 3D printing in so many places.
Yes.
We're doing the Mahler experiment at the Jefferson Laboratory, and we're holding up little blocks of quartz with 3D printed containers that we've tested them in radiation beams, and they hold up just fine. So 3D printing is an amazing, and we're moving away from the traditional methods of manufacturing in the sense that you have an engineer who makes a model, a draftsman who makes a drawing, a machinist who makes a part. You go right from the model to the part.
Yeah, exactly what I was thinking.
Prototyping,
Daniel, yeah.
It's amazing. Oh, what a great time to be alive, right?
I agree.
All right, so I'm going to do some stellar events this week. It's June 21st through June 28th. Of course, thank you, Janie, for pointing that out. It's a full strawberry moon, and the moon runs low. June 22nd.
We need to recharge it.
Okay. June 22nd, James Christie discovered Charon, Pluto's companion dwarf. You say planet, I think it's just a companion. Well,
I call it a moon because I still consider Pluto to be a planet. So meaner.
So moon. There you go. June 23rd, the occultation of dwarf planets series, visible from most of North America. You do need a telescope, however. June 24th is the midsummer day, and I don't know why that's different from the solstice. If anybody knows out there, and this is what our audience is great for, please tell us. Okay, so June 26th, the Globe at Night begins their next project. And June 26th through July 5th is when that's going to run. You want to look for either Hercules in the northern hemisphere or Scorpius in the southern hemisphere. And we understand this is a pretty important citizen science project. It's very easy to do, too. You go outside, you report what you see to their website. You could do it online. You could do it on the website or on the phone. That's what I'm saying. So go ahead and share. This is mine. Share mine. Yeah, there you go. This is the Globe at Night site. We haven't shown it for a while. And you want to go here to the Observe and then look at the campaigns. And I happen to have a tab open for it. They talk about the 6 easy star hunting steps. And every month they have a project that runs for about 10 days. Here's the one for June 26th through the 5th of July. Okay, that's it for that. So let's see what's next on here. June 27th, the moon is at perigee, and Saturn and the moon are in conjunction. In fact, Saturn is 0.1 degrees south of the moon, and there's an occultation of it visible from the central part of North America. Did I say that right?
Yeah.
Okay, good. June 28th, the moon is on the equator, and it's the last quarter moon. Also, Mercury is 4.7 degrees south of Pollux. And Neptune and the moon are in conjunction. Of course, Neptune, you're going to want optical help. June 28th is the Friday night. This is our next Friday night show. Jeff is thinking about a crunchy topic. I hope he has one by now. I don't even know. So stick around and we'll see if he figures something out. Find us Fridays at 9 p.m. Pacific time on the Everyday Spacer Facebook page and the Everyday Spacer YouTube channel. What inspires you the most for this coming week? Go ahead and take us out.
Okay, if you or someone you know has done something interesting involving space exploration, science, or astronomy, week 28th.
Did you figure something out?
Yeah, I saw a really interesting thing on detoxifying the regolith on Mars.
Oh, right.
Getting rid of the percolates and actually using some of the results of it.
Yeah, that was pretty cool.
So I think I'll talk about that and share some videos that I found on the subject. Which went into really deeply. So. Oh, good. Okay. Well, thank you, Larry, for being with us here tonight. We really appreciate that. And if you want to come back, we would love to have you. Thanks for Cliff and Daniel. And Cliff is a good show. He said it 3 times now, so it must have been pretty good. Daniel and Janie Becker. Oh, good. Midsummer Day is celebrated in Scandinavian countries. I did not know that. All right, so Janie was here, and Daniel, and Cliff, and Scott, and Happy Place was here. I know we had Dawn, so I think we got everybody, right? Yep. We like to do a shout out. And we've got Larry right here.
And Larry right here.
I thank the audience for showing up.
Yeah, so we have a really, really wonderful audience. All right, folks, have a great week. We will continue to look for your comments, and thanks so much. See you next Friday.
Good night.
Good night.
Bye-bye.